Hello everyone, this is lecture 22 of Advanced Drilling Engineering, PTRE 451545. Today we'll proceed with module 4 and discuss the project that is due tomorrow night, 1 minute before midnight. And like I said, I'm going to send an email, but there will be no lecture next week, unfortunately. And I will try to make it up to you guys, either by recording or something. Um, First, let's start with questions on the app, and then I will tell you some pointers about the project that because I received a lot of emails, and there were some common areas that I identified. Let's start with Justin since he has a question. Justin.
So I see the flow out increase, and I shut down rotation, pick it off bottom, start turning pumps off, and the kick remains under the drill bit. So both my casing pressure and drill pipe pressure actually come up the same rate and end up the same. And if I look at the kick, I see the kick is not in the around the BHA or not migrating. I just want to make sure everything that's okay.
So the question is that the SICP is equal to the SIDPP?
Yes. Which tells me the kick is completely below the bit, and there's no migration happening.
So it's staying the same all the time?
Yes.
To what value?
The 1600.
No, are you sure you received the kick?
Yeah, absolutely. I can send you the screenshot of what the kick looks like. I see gas below the bit.
And you are reading wait, let me open my app. You are reading DP pressure, that's your SIDPP, right?
Mm-hmm.
And choke pressure, the red is your SICP.
Yes.
And they stay the same value all throughout?
They do, yes.
Okay, something weird is that would be the case if your kick had the same density as your mat.
So my calculation shows the kick to be at 9.3. If I go look at the kick screen, it says 8.5.
Yeah, I mean, it shouldn't be the case. It should not be the case. Because if you do the YouTube model and you have the same SIDPP and the same SICP, you automatically have the same mat density as the kick has the same density as the mat.
Well, there's no YouTube because the kick is below the bit. I wonder if I picked up the drill string too much.
Okay, it's below the. How much did you pick it up by?
I didn't think I picked it up that much, but almost a full stand. Let's see, 90 feet.
Okay, you picked it up a lot. I would expect like something like 5-10 feet off the bottom, 15 maximum. But there is still YouTube because everything below the bit is still considered annulus. It's like a gigantic, I guess, annulus section. So I will put that on the right side, on the right leg of the YouTube model. The thing is, what was your pit gain?
6 barrels.
Yeah, you took it's a very small kick. It's a very small kick. And also you lifted off bottom too much, which I think, because yeah, if you lifted, generally they lift up to the part that they see one joint above the BOP, and there is a joint every 30 feet, right? So I wouldn't expect you to have to pick up over 25 or something feet. I would say in the app, just pick up like 5, 10 you should be okay.
Yeah, I was just picking up until I didn't have any weight on
I
bit,
think you
but
shut it in too fast.
I guess the question, should I rerun it?
Yeah, rerun it and let it flow a little bit. Remember when I was doing the example in class, I told the students that I know I got a kick, but I'm waiting a little bit so that it's not like one barrel.
Mm-hmm.
Yours is 6 barrels, so I think the difference is so small that it doesn't get detected. It looks as if you have the same density, which I would expect in your project to have higher SICP than SIDPP. Because the density of the kick is smaller than the density of the density of the kick fluid is smaller than the density of the mud.
Okay, I'll rerun it and
Yeah, try to rerun it and get some. Don't also, yeah, you know, in real life you don't really see the kick entering your well, so. Yeah, I think you are gonna hit the kick at about 18,322 feet.
yeah.
Right, something like that. Yeah, and another common problem, I'm coming to you. Another common problem is that people, when they do the estimations, you know, you lift off the bottom, so you get the kick at 18,322 or something, and they lift off the bottom to say 18,310, and you are reading 18,310 on the screen, but this is not the value that you should use as the true vertical depth. That's the bit depth. The hole depth is, the borehole depth is 18,320 something. So make sure you don't, this is gonna give you an error if you don't use the same true vertical depth. I had somebody email me last night and I realized that this is the mistake they are making.
Okay, thank you.
Thank you. Sounds good?
Yep.
Okay. In Bokun,
I was not even having a question then, but when you said the true vertical depth is 18,222 now, I'm somewhat confused because
around there.
what we have is that 18,310 as our true vertical depth when we got the key.
Okay. That you got before you lifted off the bottom?
I don't know.
If you read that,
confusing to
is it something that you read here in the top?
Yes, this is what
in the top left of your screen.
Yeah, bit depth.
Yeah, bit depth. That's where the bit is.
Okay.
But the hole is deeper. The hole is flip the screen. Well, you don't have it.
This is not the software.
Yeah, this is where the bit is. This is not your true vertical depth.
So how do we get
if you
the
lift it
vertical
off the
depth?
bottom? Huh?
How do we get the vertical depth?
Well, you get the data on where you had the kick. Basically, if you flip the screen or if you go here,
Okay.
you will see the bottom. So here, 9843 in this example, and look at that, 9843. If I increase my,
For example, this is our one and this is what we are working with.
here, okay, 18310, that's where the bid is.
So where the
okay.
true vertical depth?
Yeah, what does it say? You have bid there. There must be somewhere that says there. Go to
Well depth.
well depth. Also, you got the kick at 310. Okay. So, but then you didn't lift off bottom.
That's what. How do we lift up the bottom? Because this is the process of immediately we got the mud.
Okay, so you
the
didn't
iron.
lift off the bottom.
I off it. Then I started until it gets to 0.
Yeah.
Then I to 0.
Yeah.
0. That's why I asked last. How do we lift up the bottom?
Oh, you keep when you go this to bring it to 0, you keep pressing to go negative. That's how you lift off the bottom. So
Okay, and it's a little bit negative here, but then negative to what point?
you're gonna see this going up, basically. And there is a screen that is.
The rule says to 0. That's why.
Huh? Okay. 1 second. Okay, this is a different example, but let's do this. 1 second. Okay, I'm pumping, and then I'm rotating. Say I got, and then I am applying weight on the bead. I'm applying weight on the bead. I set the auto driller on, and then I think I got a kick. Okay, so I stop the auto driller. I go to 0, then I keep on lifting. Doesn't it? Oh, keep the auto driller on. They might have made an update now and it doesn't let you go off the bottom. No, it goes off the bottom, it doesn't show. Look. It goes off the bottom.
Yeah.
It just doesn't show
No, it
here.
doesn't show.
Yeah, so it does
How many feet from the bottom?
less than 30 for sure, 10 or 15.
Do we still need to reduce this since we
Did you lift off the bottom?
probably just a little bit because minus 0.3?
Yeah, there is a reason to lift off the bottom, not to get stuck. They do that all the time in the oil field. They lift off the bottom when they stop drilling so that you are not getting stuck.
The app is on Roxing fan, I don't know.
Yeah, okay. I mean, okay. The thing is that because you lift off the bottom, if you got the right answer, it would be okay. But if you lift off the bottom, you need to take account of that region underneath that is filled with kick fluid because it's not the annulus above it. It's, so yours may be very small that it wouldn't make a difference in the value that you calculated. If your value is the same as Kaluha's, probably it's going to give you all the points. Yeah, it's a good practice to lift off the bottom though after you stop drilling immediately. Now I don't know why now the app doesn't show. It may show when you go deeper, but I know there was an update since last year. So, but the numbers go down, which means that it's considering that you are lifting off the bottom, but it doesn't show you the bit to be lifted off the bottom. So, but the bit depth goes lower and lower when you do that. So, yeah, yeah. Well, it's a very short simulation. So, if you want to know if you are accurate or not, you can do another simulation. Don't lift at all of the bottom, and do the estimations then, and see if they are the same as. Yeah. So that must be what's happening here. But yeah, I mean. I guess a lot of stuff happened every update of the app. 2 years ago, there were a lot of problems I had to deal with. Any other questions? Okay. Now, to know that you are right or not right, let's see. Your mat weight is 9.6, right? And you have an indication that the kick is 8.5 or around 8.5. Somebody said this on another screen, which is basically an estimate based on a pre-applied equation of state. We're going to talk about equations of state later in this class. What do you expect the density of the kick to be with respect to 9.6? Be more than 9.6 or less than 9.6?
Should be less.
Why do you expect it to be less?
Because the short casing pressure is more.
It's more than the shunting drill pipe pressure. Okay, that's a good guess. What do you expect your kill weight mat to be?
Higher than
Yeah.
ground density.
Why?
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 To contain the formation pressure.
Exactly. Very nice. Very nice. You are dealing with the wrong mat weight. for that formation. And yeah, these are the things that we are trying to see with this project. I mean, okay, there are some details. That's how it is in the real world. A lot of details, a lot of stuff that you need to take into account, details that matter. But the fundamentals are what you just said. Like, I think I have a kick that is smaller density than my mat, and I had to have more mat density to drill through that. It's very simple. So you probably encounter a formation that has light fluid of high pressure, right? This is what you are going to tell your supervisor. And in the official memo. And probably there is a well-controlled team that will take over and deal with the kick, which is probably going to be people coming in, they're going to be wearing yellow suits or yellow overalls. They're going to be looking like bananas. And they are going to deal with they are going to be dealing with the kick. Okay. Now you have a pit gain, right? And the pit gain is active pit gain. So you started with 500, you made the hole deeper and deeper, and then you got a kick. So when you make the hole deeper and deeper, what do you expect the active pit gain to do? Go up or down?
It should be down.
Okay, down, yeah, because you make the hole
No,
deeper.
so-
Okay, understandable, right? Makes sense. Okay. And then you get a kick. So what do you expect to happen to the pit gain from where you are when you get the kick?
It should increase.
It should increase. Doesn't mean that it's going to go above 500, but it might. 500 is where we started.
Mhm.
Okay. And then you have okay, you lifted off the bottom. There is a portion of the kick below the bit. Okay. And you know how big the hole is because that's how big the bit is. And then you have a portion of the bit in the annulus. And you know how tall. You can estimate from the routine pipe calculations that you can estimate how tall the kick is, right? And from there, you can make the YouTube model and understand. Yeah, it's a fairly simple problem. Yeah. So, I mean, if you get a kill mat weight that is 9, you'll probably think that you are wrong. You'll understand that something went wrong. And if you get a kick density of, I don't know, 12, something is wrong, right? Anyway. Any other questions on the project? Donald, all good?
I'm good.
Okay. We are gonna proceed with what we were doing last time. Last time we talked about this whole process. You get a kick, you shut in the well. I'm trying to put everything into one list. So we said the first 4 steps is starting to drill, you wait for a kick, you shut in, blah, blah, blah. And then you make some recordings and you proceed. Now we're going to apply the YouTube model. So it's basically the same problem as we have seen before. And the YouTube model works for it pretty well because you have really 2 fluids that are very immiscible. They don't mix with each other. And then they have distinctly different densities. And yeah, you have surface pressures that you do know and you see directly. SIDPP, SICP, and you also know the mud weight very well, obviously. And yeah, so you can estimate the BHP, etc., etc. So what are we gonna do here? You have a pit gain, okay? You have isolated the pit gain as we just said earlier. And you will come up with the capacity of the annulus, and you will estimate the kick height. Now, in your app, it's close to the real world. So you have the part that is below the bit because you lifted off the bottom. You have to lift off the bottom so that you don't get seizing, get stuck. And you're able to start drilling again after you circulate the kick out of the hole. So this is more or less what you're gonna use, but in your project, you're gonna use a more complicated version of that. It is important to know in which annulus the kick is. The kick may be too high, too tall, that extends above the BHA. The BHA may also not have just one diameter. It may have varying diameter. So the capacity changes as you move up the BHA, okay? So it's not just drill collars and then drill pipe. In the classroom, we do assume that. Drill collars, drill pipe. In the app, you have two types of drill collars. Drill collar 1 and drill collar 2. So you need to take that deviation into account. That deviation in diameter into account. Now, if the wells are deviated or inclined, I should have said inclined here, correct for the inclination using this. You don't have this into your app is vertical well. So in that case, if it was an inclined well, you will be using this. Okay, the inclination angle times the height of the kick, and use a kick corrected kick height, which is not a real kick height. Is the kick height equivalent to if it was vertical, basically? And you will have to use this for your equations, but not in this case. Yeah, I forgot to say that there is two drill collars that are used in the app. Actually, if you go to the tab called on the app called let me see, well configuration, you will find a lot of information there. Liner, drill string, drill bit, gradient, mat, etc., etc. And yeah. Okay. Now, the calculations we are gonna do, we already talked about one, but we are gonna start from the left leg of the YouTube model, as you learned already from module 1, and we are gonna apply this equation to get the FPP. What I had wrong, basically. I thought my FPP was different, and it was higher than what I thought it was. So I'm gonna calculate it now with the SIDPP in mind, the stabilized SIDPP. And this is the part of the class that I was gonna say that make sure you use the right TVD, the TVD of the entire hole. So if you lift it off the bottom, make sure you use the actual hole depth. Then convert that to density using the same true vertical depth, and that will be the kill mud weight or the kill weight mud. Some people use KMW, some people use KWM. I think your app uses KWM, something like that. Okay. And then we're gonna move to the right leg, which is a little bit more complicated. It's more complicated, but if I know the kick height properly, which is a hard value to come up with in real life and in your project, then I can use the SICP that I know directly and plug into this equation. I know FPP, I know the choke pressure, the casing pressure, I know the raw mat, I know TVD, and now I know H kick. I don't know the density of the kick, and I'm gonna solve for that. And this is how I'm gonna get the density of the kick. And remember that these two are not the same. The density of the kill mat weight is not the same. Yeah, it's actually completely independent.
You sure that?
Yeah, they are not related. There is no equation relating the density of the kick to the density of the, well, that is a little bit of a false statement. Well, actually, it's you can have the density of the fluid in a formation related to pressure and temperature through an equation of state. This is what you learn in thermodynamics, etc. Van der Waals equation of state, and then there is the Penn-Robinson equation of state, and there is several more. There is one called SKR, and some others that are very well used in the petroleum industry for oil and gas fluids. But think about it, you can have gas, very high pressure, and you can have heavy oil, very low pressure. If you have gas that is very high pressure, rho of kick would be very low. Rho KMW would be very high. If you have heavy oil, very low pressure, it would be very high rho kick, very low kilowatt weight. There wouldn't be a kick in that case to begin with. But yeah, I'll add here that I would expect my rho KMW to be bigger than the rho mat. Yeah, this is something I didn't specify. Rho mat is smaller than rho KMW. Can you think of a case where this is not the case? This is not true.
The density of the mod less than the mod density of the. Is it actually possible?
Yeah. Can you get a kick not because you had the wrong mat density?
Yes.
You can swab it in.
That's one option. Yeah, you got it when you are swapping.
Probably you fracture the formation.
Yeah, or fracturing the formation. Then you have lost circulation. Then you are dealing with a different problem. You need to pump lost circulation materials to plug in that portion, circulate the kick out, and then yeah. We had this issue in the Permian Basin one time. We drilled, and there was a section that was wacky stone, which is basically very, very, not light, more like wacky stone is more than the porosity was very high. So it was more higher than what was the rest of the region. It wasn't high in general, but we were losing a lot of fluids there, and we ended up trying to pack it off, pump some low circulation material there, which was basically bentonite, to pack it off before moving on because it was giving us a lot of problems. It was either that or a fracture that we accidentally opened, and every time we were pressurizing the well, it was opening. So we had a fracture that it was like you open the fracture when you pressurize the well, and then you remove the pressure, it closes. And then, but the rock is already broken. So every time you pressurize the well, the fracture was opening. Either of, I don't know. Nobody knows what was the real cause. Now that well was ridiculous. Anyway, you can combine the two legs of the equations for the two legs of the YouTube model to get SIDPP and SICP to get the raw kick if you want, instead of using this. This is the same equation as this.
Things have cancelled out.
Huh?
I said some things have cancelled out.
You cancel out?
I'm just asking. Some things must have cancelled out to arrive at that.
What do you mean?
Like in the first equation, probably some things have cancelled out to
Yeah,
arrive
yeah,
at
yeah,
it.
yeah. But this is what Justin was asking, and I told him if your SIDPP, and I forgot the P here, is equal to the SICP, that means your density of the kick is equal to the mat density. You understand why now? Because and I apologize for the typo. You understand now that your basically it becomes the fraction becomes 0. So this becomes equal to this, but this is not the case. It's because I guess he didn't let a lot of kick to get into the hole. Or you have a very small kick volume, I guess. What I was gonna say though about the, oh yeah, now you are dealing with a low density fluid, you understand, and I think you understand that it's gonna move, even if you let it alone, it's gonna start moving upward. Now, if it has moved upward significantly, you have purple above and below it. You need to take that into account. Okay? Purple above and below. You need to, yeah, purple here and here. If it has moved, you have 3 components that you need to add up for the right. Like it becomes more complicated. Or sometimes you get a kick, you're moving it up, and then you make a few mistakes and you get more kicks underneath. So you need to take those into account. And in real life, you don't even see the kick. It's not like you can flip the screen like I did now and see where the kick is in real life. In real life, you can do like 10 circulations just to make sure that you circulated everything out instead of just 1, you know? Anyway. Initial conditions after well shut in with kick at the bottom. Okay. This is gonna be very similar to homework 5. You will see that, and I will upload the homework either this weekend or Monday. Before I leave for Oklahoma City for sure, I will upload it. For the initial conditions after well shut in, the kick column may be taller or shorter than the drill collar length. And taking the angular volume opposite of the drill collars, we call that DCAV. H kick is calculated by this equation. This value 1029.4, you have seen it before, right? Okay. And this equation assumes that the drill collars are one type all along, right? Drill collars is basically the BHA. And you assume that the BHA has basically one outer diameter. But you may have varying in your app, you have 2 drill collar types. So it's not that simple. Okay, you have drill collar 1 and drill collar 2, they have different outer diameter. So you need to take that into account. In your homework, it wouldn't be the case because you're going to have to do it in Excel. And I don't want you guys to waste your time on that. In the homework, I want you to focus on the fundamentals. So this is how you can find the height of the kick. If the drill collar angular volume the pit gain divided by the drill collar angular volume is less than 1, it means that the kick is below the drill collar. Let me draw something to make it clear for you guys. This is my well. This is my drill pipe. This is my drill collars. I ignore the bit, okay? The bit doesn't have a height. If I'm in a situation like this, look at how big my kick, how tall my kick is. My kick doesn't exceed the drill collar length. Okay, my drill collar length is this much. My kick height, this is LDC. My kick height is this much, H kick. So what do I have now? I have a situation where LDC is bigger than H kick. Okay, so this is true. And therefore I use this equation. Or a more complicated version if it's if I have two types, etc., etc. But what if my kick is taller than the drill collar? What if my kick is like this? Now my kick is this tall. This is reversed. And now I have two annuli for my kick. I have the annuli opposite of the drill collars and the borehole, and the annuli opposite of the drill pipe and the borehole. Okay, now I'm much more complicated. I'm much more complicated. In that case, I have this, right? And what if I'm in this situation? Oh, we lost the drawing. Yeah. Oh, there you go. Okay. What if I'm in this situation? Now, my kick started moving, and I have this. It's moving up. So my kick height is now this, but it doesn't coincide. I have mud underneath it. No, I'm even more complicated, right? You need to take all this stuff into account, especially if your kick is moving.
Is in the feed, like this app, it records the height of the kick, and I find out that from my calculation, it's almost the same. Is it also like that?
Well, the app assumes an EOS model for the kick, but the app put the kick inside the app. I mean, how do you know you are really never sure what kind of fluid you are dealing with. And even if you have data from nearby wells, it doesn't mean that the values that you have, the data that you have is representative of what.
So that means it's not possible in the field to have the height of the kick. Maybe
No, you
read
have the height of the
something, something without calculating that.
You think you know, you make some estimations, you have a range. Yeah, you have a range, but you're never 100% sure. Just like you are not 100% sure what the FPP is. You don't know. You know what the mud is because you read it from the surface. Okay. You know what the SIDPP is. You know what the SICP is because you ask somebody to be recording them for you. Okay, and they are reading them from the surface, but and you know the pit gain, but you don't know anything else for certain. And hopefully you know what is the BHA look like. Sometimes there is people who run the BHA downhole, something happens and they need to see the design of the BHA, and you ask to see the design of the BHA, and they don't have it, or they are not certain. Yeah, because like when you have to go fish something, and you want to say, okay, this is where we got stuck or something, this is where we cut. What kind of tubular do we have where we cut? And they don't know because there was no, it doesn't happen anymore, but there was no design cap of the BHA before they ran downhole. And yeah, but obviously you need to know what kind of drill collars you have, what outer diameter they have. The BHA in real life is much more complicated than a set of drill collars of fixed outer diameter. Sometimes it takes a whole tower, a whole shift, 12.5 hours to make the BHA. And then it has to go up the rig floor with a forklift and run it in. It takes, BHA is very, very important. It's the most expensive part of the drill string. Anyway, okay, these are the variables. This is what you need to use for your homework 5. But homework 5 is simple in the sense that you have only one type of drill collars for the BHA. How much more barite to mix? Okay, so now you know the mud weight, the kill mud weight. So you need to increase your mud weight from 9.6 to whatever. How much? You're not gonna tell the mud engineers, Hans. You're gonna tell your mud engineer, we need to increase the mud weight from 9.6 to 13. Okay. The mud engineer will say, okay, this is how much barite we need to mix with this much water to get to that value. And this is the equation he's gonna use. The mass of barite needed to be added in pound mass to a total volume, blah, 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 this equation. And then the volume increase is given by this. Now, he's gonna take this barite and he's gonna divide it into number of mass of barite per sack. And he's gonna tell the people that work for him, that work under him, mix so many sacks of barite in this volume of water, or the base of the mud that they are using, etc., etc. Now, if you are using oil-based mud, things are a little bit more complex because many times the kick fluid would be mixing in the mud. So things change with time as well there, because mud is mixing inside the oil-based mud. If you have gas kick, for instance, it's hydrocarbon. And then oil-based mud is diesel or an oil-based or whatever, which can mix with the gas, right? And create a miscible phase. That makes things much more complicated. You need to make adjustments to the YouTube model, etc., and time matters. When I was doing I think I told that story, when I was doing the well control certification, we were using oil-based mud. And things were changing, even in the simulator. That was 12 years ago. We were so slow in our process, I think we were pumping up with 20 SPMs instead of 40. Eventually, by the time the kick made it to the surface, there was no kick anymore. It was in the mud. It was in the mud. Anyway, this is the incremental, the volume increase. Okay, now, I think I have this animation here. Before the kick circulation, now I'm moving into the next part. I'm gonna try to circulate the kick out of the hole. How am I expecting the kick to behave as I'm moving up the hole? I'm expecting it to, what I'm expecting is pressure to do. What I'm expecting the pressure to change as the kick is moving up.
It's increasing.
Increasing?
No, it's decreasing.
Yeah,
It's
okay.
decreasing.
So how do you expect the size of the kick to change moving up?
I believe it should expand.
Huh?
The volume should expand.
Okay, so fatter, taller, shorter, slimmer, what do you expect?
If the volume is increased, it could be taller.
Very nice, taller. And then, I mean, how far it is, I guess, depends on the annulus there. But
Mhm.
you are expecting it to become taller
Mhm.
as it goes up. Okay. If it becomes taller, okay, it becomes taller. It takes more space.
Mhm.
It has a lower density than the mud.
Mhm.
Remember, in the YouTube model, it only cares about the height. It doesn't matter about the hardness or something. Like everything depends on the height, hydrostatic. Okay? So how do I expect the SICP to change as the kick is moving up, if the kick is getting taller and taller as it's moving up? How do I expect my sharding casing pressure to change as the kick is moving up? And beyond your project, now you don't have to do that in your part A of the project. I'm asking, you have to do it for the homework and part B of the project. But yeah, what do you expect to happen to the SICP as the kick is moving upward?
I believe the price should increase because you said the last class.
You said increase, right?
Yes.
Yes, okay. So when will this SICP be the highest?
And the surface.
When the kick is on the surface? Okay, what part of the kick is on the surface? Huh?
The lowest part of the key.
If the lowest part of the kick is on the surface, that means the whole kick is on the surface. It has flared down. You burn it at the, yeah. When the top of the kick touches the surface, that's when the pressure is the highest. And then you start burning the kick. If you have the sound of the simulator on, it's gonna be hearing like shh, like it's making the noise of the flaring. And okay, you touch the top of the kick touch the surface. That's a high value of the SICP. And then you start burning the kick. What will happen when you are burning the kick and replacing it with mud, basically? What do you expect to the SICP to happen?
Begins to come down.
Okay, calm down, comes down. Yeah, I agree. I agree. Very nice. And once the whole kick is out of the well, what do you expect the SICP to be equal to?
That's what I did.
Yeah, yeah. Excellent, excellent. Okay. Then I have the whole well filled with mud. It's the wrong mud, but it's under control because the well is shut in. Okay, very nice. That would be my first circulation. So if I'm gonna get an underground blowout, it's gonna be a fracture at the casing shoe. That's what the underground blowout is, a tensile fracture. Same as hydraulic fractures that we do in the other class, in the advanced stimulation class. Okay, when is the most vulnerable moment that I might get a fracture? When I'm circulating the kick out. When do you think, if I get a fracture, when is it most likely that I would get it? When is the most dangerous point that I'm gonna get it? No, it's gonna be at the casing shoe. That's the location. But when the kick is at the bottom, all the way up,
I think
out
the
of
surface, not the surface.
okay, what part is at the surface?
The top of the key.
Yeah, when the top part of the kick is at the surface, that's when my SICP is higher. So I'm always looking at the SICP, trying to keep it below a certain threshold. Okay, say there is a threshold, we call that MAASP, maximum allowable angular surface pressure. My kick is moving up. I look at SICP all the time. My mass is 1,000. My SICP is 950. I'm getting there. How do I mitigate that if I'm getting there? I'm approaching that the 1,000 value, which is my threshold, making numbers easy for you guys. Well, what can I do to mitigate that?
And the well is shorting.
The well is shut in. I'm circulating at a slow rate through
You can increase the circulation rate.
decrease the circulation rate. I can do that, but that would be my last resort. I don't want to change the circulation rate throughout the process. I will open the choke. I will open the choke to release pressure. Now, if I have the choke 100% open and I'm still approaching the thing, then I will need to do that. Okay? Because I have no other option. You are left with no other option. Okay. Now, okay. What about when do I get more kick? When I'm circulating out of the hole? When do I get more kick?
When?
Would I be getting more kick? When I'm circulating out of the hole? When am I going to be getting more kick in my well? While I'm circulating the kick out of the hole, is there any point where I have too low pressure, too low SICP, and I'm going to be getting more kick inside the well? What is that threshold, the minimum threshold? What is the floor value?
Of the pressure in the well.
Yeah, on the annulus.
On the
That if I'm below that, I'm gonna have a kick. Do you think?
That should be.
If I ignore the presence of the gas, for now let's ignore it. And if my kick is not there, what is the pressure that I need to? I'm missing. Yeah,
And it's nothing.
yeah. Imagine I have only mat. What would be the pressure I need to be above so I don't get a kick? Yeah, pressure on what is down on the surface.
Okay,
Yeah. Okay. So if I get below SIDPP, I'm in trouble. Actually, it's not exactly like that, but let's stick with the simple case now, just to show you something. Okay, I'm approaching that. SIDPP is 500, making easy numbers, and I'm at 530. What can I do to fix that? I don't want to drop below 500. I'm gonna get a kick. What can I do to fix that?
Yeah, 530.
Operationally, what can I do?
Increase the mod weight.
No, I cannot increase the runway. It's gonna take.
Can you increase the drip pipe pressure?
No, I'm looking on the annulus.
Analog.
Now, it's the SIDPP value, but I'm looking at it on the annulus side. So the SICP becoming lower than the SIDPP. And I'm getting there. It's like I'm 530, and I know at 500 I'm gonna get a bigger kick. I'm gonna get more kicks. What can I do? Based on what operations I have in my hand, what can I do to avoid that? To take the pressure higher, make the pressure go higher. The pressure that I control, the SICP.
Circulation rate.
Again, that's the last result. What did I do before?
You can close the choke.
I will close the choke.
So you include it.
Now, if I close the choke too much and I still cannot, maybe I increase the flow rate, but that would be the last resort. And that would be very dangerous because if you close the choke, you don't have an avenue for the mat to leave, for fluids to leave the well, and you are still pumping. That's how you get underground blowout. Because you are just pumping on a closed well. That's something very dangerous. Yeah, you'll be very, very careful for that. Well, yeah, basically opening and closing the choke, this is how you keep the pressure within the levels. And actually the lower limit, the floor is not exactly SIDPP. I just tried to make things simpler for this example. I just wanted to show you that you are gonna use the choke to manipulate that, but very nice. The kick will be circulated out using the predetermined designated slow pump rate. Probably your company has a policy for the pump rate, the slow pump rate that they are gonna use, and you are gonna use that. Now, why you don't want to change it, you will see why later on. Because, actually, it's because you already gathered data on that slow pump rate. You measure the frictional losses on that pump rate before you started drilling. So you have information on that 40 SPM. You don't want to go with 50. You don't want to go with 30. Since you don't know the frictional losses at 30 or 50. That's why before you started drilling, before you even got the kick, you measured the frictional losses. Did you do that for your project?
The frictional losses.
Yeah. You see, you always measure the frictional losses before you start. You just run the. You just circulate without rotating and wait on the bit, so that you, like I did in the first video I showed you guys when we started drilling.
We just
Circulate and rotate.
Then apply with
Yeah, or not even rotate, just circulate and measure the 40, measure the DPP. That is the frictional losses throughout the pipe, the system at that rate. And we did it for 40 and we did it for 100. And we said we are going to be circulating out the kick at 40 and we're going to be drilling actual drilling at 100. And this is why you need to know the frictional losses at that point. Always before you start drilling, you need to do that. Oh, there was I think there was an animation here. No, okay. Animation, come on. Never works. Let me, there you go. So you see it's moving up, right? As it's moving up, it becomes taller and taller. You don't see it getting taller, but it was, I set it up to become a little bit taller as it's moving up, right? And as you move up, the sharding casing pressure becomes bigger and bigger, right? Because it's what you guys told me earlier. Now you're going to circulate it with 40 SPM. As fluids are circulated through the well, SIDPP and SICP, I should say the SIDPP and SICP will keep changing, and with them, the pressures all throughout. SIDPP is likely not to be changing, but could be in the first circulation, obviously. In the second one, it will, but use choke management, what we discussed, to avoid taking more kick. You take more kick when the bottom hole pressure drops below the FPP, right? It's understandable. And you use, and also to prevent fracturing of the casing shoe, that's basically underground blowout, what we have discussed. Okay, so you're going to use the choke management for that. You're going to move the choke accordingly and get the kick out of the hole. Once you get the kick out of the hole, you need to, you're not done. The well is shut in, you are safe, but you don't have a kick to deal with. You burn it out, it's in the atmosphere. You cannot open the well. Okay, what will happen if you open the well? What will happen if you open the well after you circulate the kick out? What is the SICP once the kick is completely circulated out?
It's equals to the SIDP.
Okay, so I have SIDPP on both sides.
Mm.
Okay, what does that mean?
The drilling mode is on both sides of the, both in the
Yeah.
drill pipe and in the annulus.
What about the drilling man? Is it the correct one?
No.
Okay, the drilling
Okay.
is not the correct one.
What would be the case? What would be those pressures if it was the correct one?
0.
It would be 0, 0, both of them, right? They are not 0, they are SIDPP, both of them. So I have a problem still. I need to replace the mat with a new mat, the kill weight. And I'm gonna start doing another circulation for that. So I'm not done. I'm halfway done. Okay, circulating pressures. This is what we are talking about. Knowledge of the parasitic frictional losses, delta px, helps a lot for predicting the SIDPP variations. If you circulate with old mat weight, then the initial circulating pressure on the drill pipe is SIDPP plus delta px. Okay, what is the delta px? It's a parasitic friction losses. How do I have this value?
We calculated it.
No, we didn't calculate it. You measured it before you started drilling
Frictional pressure loss, right?
at 40. And the slope rate. It might be 50 for your company, it might be 60, it might be 20, it might be, I don't know, 30, not 10. It will be 10. 10 is too slow. I have seen 50. I don't know if I have seen 60. Anyway, so this value I know it. And this value I see. I add them up. This is when I'm starting to circulate. I'm expecting to have this SIDPP plus delta px. Now, if you circulate with kill mat weight, then delta px has to be adjusted to provide the final circulating pressure, as we call it. Now, before you start drilling, it's before you got the kick, right? When you started drilling, you didn't know that you're gonna get a kick. So you didn't know the kill mat weight. You find it now in your part A of the project, right? You are calculating now. You didn't know you are gonna get a kick. So you didn't know the parasitic frictional losses at that kill mat weight before you started drilling that section. So how can you estimate it based on what you know? You measure delta px. Now, it was at raw mat. Now you have a raw KMW to deal with. So you're gonna take the delta px and multiply by the raw KMW and divide by raw mat. This is not an accurate, an exact estimation, but it's good enough. Okay, it's an approximation that we are doing. We take delta px, say your kill mat weight is 12, your raw mat is 10, and you multiply by basically 1.2. Okay, this is just an estimation, approximation to make your life more predictable. Okay, an adjustment. You understand the logic behind it? My kill mat weight is bigger. I'm expecting the frictional losses to be bigger, but I don't have a direct indication for them. I have a direct indication for them at a lower value, and I'm going to use that to adjust. Very, very straightforward, linearly. Yeah, what I was going to say. Any questions about this? I think it's logical, right? What we try to do. Okay. Now, also, I am, how do you call it? In real life, I don't have the app. I cannot shift the screen and see where the kick is, right? So how do I know how much I pumped? how do I know if I pump enough to make the whole way from the bottom of the well up, right? How do I know I pumped enough
Of the key weight
of any mud?
anymore.
How do I know how far I pumped? I don't know in real life. I don't know I don't know if I have a kick. I don't know how the kick looks like. I don't know how many kicks I have. I know I'm pumping. I know how much I pump. But how to, in terms of barrels, how do I know if what I pump is enough to cover the whole distance from the bottom of the well of the annulus to the surface? How would I know that from the me standing in the
Surface.
surface?
From the pressure.
No, not from the pressure. Something else that I can read in my screen.
It's still not the pressures.
No, I read the pressures, but how do I know? I mean, okay, we said,
I think we have said if we don't have any kick, then the
yeah,
high pressure
but
and the
still,
short should be the
how
same.
do I know that that the same when the kick is out of the well? How do I know I circulated enough to make it all the way up? I may see the same pressures, but I might be halfway, you know? I might be using the wrong density. Yeah, I might be measuring. How do I know on the surface how much I pumped in terms of?
You know what you're pumping, you know what is returning.
Yeah, but in terms of
Look at the bottom.
in terms of time as well. Where is the aspect of time? I'm pumping strokes per minute. Okay. And the flow rate is gallons per minute. I can convert that to gallons per stroke if I want to, right? Or barrels per stroke or barrels per minute even. I don't need to do barrels. Barrels per minute we do in fractioning. Okay, how do I know how far I am in? I will count strokes. So if you see your app, you have where is it? I can see the app. Go to the home page of the app. You see SPM has to do with the rate and pumping. And then next to it, if you have strokes, and it's a number that goes up with time if you are pumping more than 0, I guess, strokes per minute. So if I'm pumping with 5 strokes per minute, after 1 minute, what is called my stroke counter gonna say?
5 strokes per minute. After 1 minute.
Yeah.
That's 5 strokes.
Yeah. What about 2 minutes?
Okay.
Yeah. And so on and so forth. So I will use the stroke number to know how far I am. Also, I will, what I was going to say, I will, there is a button next to it, next to the stroke counter, yellow R. Okay, this is the reset button. If you keep that, if you press that button, stroke count goes to 0. So before I start circulating, I will calculate how many strokes I need at that 40 stroke per minute slow pump rate to make it all the way up from the bottom, all the way up the hole, or from the drill pipe down. And I will make that, press the reset button and start at 0. So if I want 1,000 strokes to make it up the hole, I will press the reset button to 0 and start counting when I start pumping, right? Just gonna start 1 stroke, 2 stroke, 3 stroke. At 1,000 strokes, I know I did 1 whole circulation or something, right? Okay, it makes sense, right? because in the real world we cannot see where the kick is, the number of strokes can be used to see how far along the well all the new mats have been circulated so far. Do not forget to reset the strokes number before each cycle when you do your simulation. Number of strokes to fill the drill pipe is this equation which you have seen before, right? We have seen before in this class? Okay. We have seen in the other class. If you use the in useful resources document, I gave an equation sheet from University of Texas. It has the 42 at the denominator. It's wrong. This is how it should be. Just saying that if you use that equation, it has a mistake. So use this one. 42, you know why 42?
No?
42 gallons in 1 barrel.
Okay.
Okay. Now, VDP is the volume inside the drip pipe in barrels. And VDC is the volume of drill collars in barrels. I ignore the bit. And then 42, you know, gallons per barrel. And then Q pump is gallons per stroke. That's why you need to go from barrels to gallons, and then you divide by gallons per stroke. But you can have GPM, gallons per minute. In that case, you need to divide by the SPM value. So you divide, if it's gallons per minute, use the 42 to go from barrels to gallons on the numerator, and then on the denominator, divide by SPM, strokes per minute. And then you're gonna have basically sorry, in the denominator, divide Q pump with strokes per minute. So you have gallons per minute, and you divide by strokes per minute, so you have gallons per stroke, and the gallons cancel out, and then you have just stroke on the. So this value is gonna be a number of strokes to go down the drill pipe, and this value would be a number of strokes to make it up the annulus. For reference, most of the wells, it really depends. It really depends. You may have a very narrow annulus, you may have a very thick annulus. So it won't be the same value. It won't be the same value. It would be different, but you need to know it. Something like could be like 4,000 strokes to go down hole from the drip pipe, and then 4,500 to go up. So a whole circulation is 8,500. So don't forget to press reset on your app before you start pumping, so that you know how far you are. In real life, you cannot see where the key is. So I think one more slide and we're done. Preparing for kick circulation. Knowledge of the fracture pressure at the casing chute depth is important. That's what you learned in module 3. Assuming perfect casing integrity, we don't want the SICP to exceed this maximum allowable surface, annular surface pressure. This is how we are going to calculate it, okay? A P-frac minus 0.52 times the EMW of the mat times DCSG. Sometimes they don't use EMW, they use this. It's okay though. Why is it okay?
Because we are in most times when the well is shorting,
Yeah.
when you took a key, so maybe the density of the mud could be approximated at it.
But you are
EMW
it's shutting, but you are still circulating.
or you are still circulating. So it may
Which
not
is
be
bigger?
accurate.
What is the only difference in these equations?
The difference is just the EMW and the density of the mass.
Which is bigger?
Between what?
Which is bigger between the two? This or this?
EMW.
The EMW is bigger.
Bigger, yeah.
Which will lead a bigger value for mass? Using EMW or using rho?
Rho. Using rho.
Okay, so I'm safer if I use rho or if I use EMW.
When you use rho, you are
Yeah,
saying.
yeah. So it doesn't matter. I don't need to worry about EMW. So most of the books you are gonna see this second equation. That's why, because it's safe. Choke management can be achieved by keeping SIDPP and SICP within predetermined ranges. And the calculated initial circulating pressure and final circulating pressure approximations can be used a priori in advance. It means to predict in advance the pressure behavior on both the pipe and casing sides. Okay, and with that, we'll proceed in 2 weeks' time, or I will make a recording or something. Okay, I will post the homework. And either this weekend or tomorrow or Monday, before I leave for Oklahoma City, it's going to be the last homework. And then we have the next part B after that. Make sure you do your part A of the project excellently. Give every information that you can to the TA. So who is your supervisor basically, so that I want everything that you can give him with the information that you have. And with that, thank you very much. I will see you all in 2 weeks, and not next Tuesday, but the one after.